Right. We've had some extremely important organizations and people speaking at this conference over the last 3 days. Well, this just about caps it for me. I was explaining earlier, I've had a lot of engagement in discussions and debates about quantum computing and its impact on cryptography. And that this is the global, but effectively, I don't know if it's in theory, but effectively the global standards bodies for deciding on the crucial question that we're all going to be impacted on about the impact of quantum computing. But I don't suppose you're going to be talking about that this morning. So I'll introduce, and are you, actually, are you a government-run body, or are you, you are part of the US federal system, yeah. But perhaps you can explain that when you speak. Yes. So Kate.
Okay. So good morning, everyone. Let me first introduce to you Patrick Grother. He's my project lead. I'm Kai Hanaoka. Today, we're from the US. We worked at NIST. For those of you who don't know, NIST stands for National Institute of Standards and Technology. Today, we're going to present to you one of our ongoing benchmark on face, age estimation, and verification technology evaluation. So this is a quick snapshot that we're going to talk about. Who are we? How have the technology improved since we started the test? Some challenges that we run into, and what's the next step? So first, I want to share this infographic with you. We borrowed this infographics from one of our US colleagues at the Future of Privacy Forum. We like pictures. It really explains this whole age assurance landscape of what it's about. And we want to use this to highlight what we at NIST do, focus in this area of work. We do biometric. We use biometric to do age estimation using face. We also have a different set of tests that does facial recognition. And for today, we're just going to focus on age estimation using face. So this is a quick snapshot of what else we do as a team at NIST. Face recognition has been ongoing for a long time with us. And then also we have iris recognition testing. And of course, the most importantly is the face analysis part for age estimation, along with a couple other tests that we do. Our test, it's independent. We run in a very large scales with millions of images, millions and millions of images. Our style of the test is black box. We don't want to know your code. So then we can protect intellectual properties. It's repeatable. It's open to everyone in the world. This is a quick workflow of how this submissions or participation works. As a developer, you sign your participation agreement, you build your software with our C++ API. We provide a validation code, including some images, so you can test your software before you submit it to us. And also it can help eliminate some of the basic bugs that you might run into. Once that's done, encrypt it, send it to us from using our submission form. Once we get it, we'll run it with all the data sets that we have. We try to always publish new data, new results every 4 to 6 weeks, but that depends on the schedule. Sometimes we take vacation, we're sick, or some hardware maintenance scheduled happen. As for ongoing, participants can submit as often as every 4 months. So avoid training on the data, but that's how we run it in an ongoing mode. But if you didn't get that, it's all on our webpage. There will be a QR code coming up, so just stay put. So let's see. This is a quick timeline of what we have so far, but I'm going to go to this one to talk about it. So back in summer of 2023, we announced the restart of this test. Back in 2014, our colleague Mayon and Patrick have done a one-time study on age estimation, but it was just like a one-time publish a report and that's it. And then almost 10 years later, we restarted the test again. In the same year of 2023, we opened for submissions. We got 6 submissions from 6 developers. The first report came out in May of 2024. And then last year, we updated the API. So what's the difference between version 1 and version 2 of the API was Version 1, we required all developers to implement all the 3 functions that you see on the screen. But last year, we decided to make function 2 and function 3 as an optional. But we encourage developers to implement those 2 functions if you have a very different way of doing this technology besides just doing a number age estimation. Today, we have about 41 prototypes in-house. That's a total of 24 developers. Half of those developers have submitted more than once. And so we're still keep going. These are the 4 data sets that we use from day one. We have very diverse data sets. They're counting into number of millions of images. Visa was used back in 2014, so we could do an apples to apples comparison just to focus on the technology, how have it improved since. And then we use various of different data sets for different measures. For example, application, we do it for the demographics, how that affects age estimation. And we also have looked into how image qualities affect age estimation using the border data sets. In the past year and a half, we added, besides those 4, those are the baseline data sets that we use. We've added 2 new data sets in the last year. One of the latest one we added is the high resolution mugshots. How we measure high resolution images. We don't do it by width and height because you can have a very big image but very tiny head. So we measure it by using the inner argular distance. That is the distance between the 2 eyes. And that way we can be sure that there's a face, in the picture that's considered high resolution. The total images, we have about 1.5, almost 1.5 images. But because we only want to focus on how can high resolution or resolutions of the images change for age estimation, so we kind of subset it and focus on just white male between age 18 to 30 to eliminate some of the side effects. And that still total up to almost over 900,000 images in 6 different inner argular distance group. The other data set we've added last year is the videos. That's enabled us to measure the variability on age estimation. This is, when you come to our website, we have a leaderboard. There are 6 different tabs of different information and results for the submissions. And Patrick will go over some of them very soon. So one of the biggest questions we have when we start planning the test is, will the technology improve? How are they doing since 2014? In our report, in our report back in 2024, we predict that the performance will improve, just kind of following the pattern of face recognition when using AI and computer vision. And you can see in this figure here, from 2014 to today, the numbers are declining. And we're measuring just using the mean absolute error, and the smaller the number it is, the better. And we can see that back in 2014, the best algorithm has a mean absolute error of 4.3. Then when we first published the results in 2024, that number have already went down to just over 3 years. And as for beginning of this year, we got new algorithms, and that number have came down even a little bit more. And that dotted green line, Patrick will fulfill that curiosity later. So half the developers have submitted to us more than once, but there are a few developers have participated multiple times. Here we have Rank Run Computing and Yoti. They've submitted to us multiple times, and that enables us to look at how have their software changed and improved over time. So we have 12 demographic groups here. We're not here to compare how each group have high errors compared to the others, but we're just looking how have the technology improves. And we're seeing improvements in each of the demographic groups. So we're hoping to be able to continue to measure this down the road. And at this point, I'm going to hand it over to Patrick.
So yeah, good morning, good afternoon. So we've seen these gains. This is a chart out of the Australian report that was presented, I think, yesterday. And that's Yoti's longitudinal gains over time, as measured by the Aussies on an Aussie data set. And so our numbers sort of tally with their numbers quite well. This is a snapshot of our leaderboard for just Yoti, and this is the figure that Kai just showed you. All the demographic groups are all trending in the right direction. The standard metric for reproducing performance, for stating performance, mean absolute error, is going down. Some demographic groups are still higher than others, and we have some uncertainty estimates on these things. But you'll notice women and men are the largest category of difference. And that is a persistent topic, and that applies pretty much across all algorithms, not just Yoti, but many, many others as well. Why that occurs is a research question, really. And I'm sure the developers think about it and look at it. But yeah, we've quantified it. That is our standard leaderboard on our webpage, color-coded. Green is below 2 years mean absolute error. And then we have some colors indicating worse rates. The numbers were maybe a bit too small for people in this room to see, but that is a snapshot of our leaderboard. Now, can we do better? So if we just go back to this one slide, we're trending down, and we've got error rates down below 2 years mean absolute error in some cases, but can we do better? Now, it's I was on this stage 2 years ago, and I said, for sure, the developers are going to leverage AI in clever ways, and they will do better. And it turned out to be true, because 2 years ago it was around about here, and things have improved. So I was right. Now, can we get further gains? So one quick way to do that is to say, well, maybe if we throw 4 algorithms or 2 algorithms at the problem. So my face goes in, we run Encode, we run Yoti, we run Cognitech, and we just take the average age, right? That is the simplest, dumbest fusion rule you can possibly think of. And that's what that formula does. The big blank space on the right hand of this screen is a different concept, which I'll get to in just a second. But if you run fusion, you can fuse 3 algorithms, 2 algorithms, 3 different ones, or you can fuse 4 algorithms. I could have fused 8 algorithms. And I'm not claiming that I've fused the best ones necessarily. I chose leading algorithms by some metric. And that's the regular leaderboard. And this is the fusion results. And the prevalence of green shows some improvements. But the mean absolute error is dropping by about 5%. It depends on which demographic group, depends which algorithms you fuse together. But a small change in mean absolute error actually gives you bigger changes in the other metrics that you would think about, like Challenge 25 or age verification, which I'm going to get to a little bit later. So there are gains, and these gains are fully realizable. You could do this today. It might be expensive. Maybe we'll have some corporate mergers. Maybe people will exchange code and just realize this is a good thing to do. Maybe they will fuse algorithms a bit more intelligently than I did. And there are ways to do this. Maybe you use one algorithm on women and another algorithm on men, and you run some sex classifier ahead of time. Maybe. This is a research problem. I'm an evaluator. It's not my job to do this in an optimal way. I'm merely pointing out that there are potential gains. All right, now there's a thing that's common in the academic world, which is to put together a thing called an oracle. This is nothing to do with a California company. This is everything to do with the oracle at Delphi, right? Greek mythology. And in this case, we put together a fusion, if you like, an oracle, but it's not it's a thought experiment. You can't do this because you need the true age. So what it's doing is it's saying, I'm going to run 4 algorithms, and I'm going to choose whichever age estimate is the best one. Of course, you don't know which is the best one when you have an image, somebody standing in front of a system. You don't know which is the best age estimate because you don't know ground truth. But it does give us a thought experiment on how good things could be. And if you could magically discern which algorithm to apply on which image, then you could get very, very substantial gains here. Instead of a 5% reduction in MAE, we're getting a 50% reduction in MAE. MAE is about half of what it would be. And again, you can do Oracle 2, just switching between 2 algorithms on the fly, or you can do Oracle 4, switching between 4 algorithms on the fly. And you get substantial gains either way. Now, can that be realized in real operations? Probably not, but it's again, it's a sort of a high watermark that researchers could reason about and think about in terms of potential. And the reason to think about this a bit more closely is that different algorithms are doing different things on men, women demographic groups, people with beards, people with glasses. All those strengths and weaknesses are something that developers can reason about. All right, so to complete that curve, we're future looking, future gains. It's a question mark, it's a conjecture. I don't know that any developer is going to realize this. We hope so. Our benchmark stays open for developers to come back and demonstrate these gains on fixed data sets. Okay, so demographics, we said, is a problem. I'm going to flick back to this slide in just a second. The way we look at demographics is we have data set that comes from an immigration setting, right? We've got millions, tens of millions of photos from immigration processes of the United States government. And they come with metadata. Now, unfortunately, they don't come with ethnicities within countries. What they do come with is country of birth. So if somebody says they're born in Somalia, it hasn't had a lot of transnational immigration, like France, like the UK, like the United States. But we use it as an indicator of something. And then we group them a bit more to increase our data set size. We group them regionally. What we don't do is just say this person is African or this person is Asian. Those labels would be too low resolution. And we don't have this. We do have this, and we could break it out this way, but we use this instead to make the tables a bit more tractable. But one of the developers has a statement on the website. It used to be on the website. NIST uses geographical regions as a proxy for skin tone. That is entirely wrong. The phenotypes evident in faces from these countries, skin tone is one of the phenotypes, but there are lots of others. Prominent cheekbones, square jawlines, bushy eyebrows, aquiline noses, all those things that make up faces are in some part genetically driven and locally driven. So using a label like country of birth or region of birth is not just about skin tone. And we see demographic differences that transcend skin tone. So skin tones in China and Eastern Europe aren't that far apart, and yet we see differences. So it's not just skin tone. But I don't care whether you regard this as ethnicity or demographics. If you've got a database, if you're running an operation, if you're a social media company or you're a government or you're an employer and you're running age estimation for some reason, and you have a database, and that database has some metadata about the people, then it's due diligence on you during some kind of operational audit to go look at those things. And if you can find any group, any large group that have got materially different error rates, you should go fix it. Could be tall people, could be bearded people, could be tall, bearded people with glasses. They're not demographic groups, but they're groups. And if you can find those groups, flag it to your research people because there's an error rate there that needs to be reduced. So we use demographics because it's expedient. We've got the data. It's available in volume, and it's got something to do with the big topic of AI bias. And we look at this in face recognition. We look at it in age estimation. Going to switch gears now and talk about noise. In the academic literature, they call these nuisance variables. But what we did, and it's in our report today, is we took a 30-second video clip of a 60-second video clip of me, 30 frames a second, 1,800 frames. And I do various things. I take my glasses off, I frown, I smile. And age estimates have variability about the ground truth line, which at the time I was 57 years old. All right? And these age estimates that bounce around in an unwelcome fashion. Right? They should stay utterly constant. Now, Yoti was in this stage, I think, 2 days ago, and they talked about this. The fact that you're wearing glasses should not affect your age estimate. And yet you can see most algorithms, I look older and then I look younger, plus noise. This noise is unwelcome. The face recognition industry learned to avoid this noise. They trained algorithms to see through nuisance variables and just hone in on identity. The same, I think, is possible for age estimation and is happening. Okay, you can look at that same trace for all of the algorithms that we produced, and we distill it, I think, into a summary number as well. But noise, I think, is relevant to day-to-day operation because we're not all presenting passport photos to age estimation systems. I went through this process 48 hours ago. I got rejected many, many times by the liveness operation. I went into the hotel bathroom to do it, a lot more light, and I passed first time. But lighting is part of this noise landscape, and you would like immunity to directional lighting, some shadows, glasses, distortion, distance from the camera, all of those things. Another topic that we are thinking about, and this is outliers. So this is my colleague, May, and 4 different algorithms, the raw image or the cropped image. That's me on the right, looking not particularly good. But May gets underestimated by 3 or 4 algorithms, one of which is by 10 years. 10-year misunderestimate. She's quite happy about this, right? I'm underestimated pretty consistently by about 2 years when that photo was taken. So, I need to moisturize more or something. But there's a little bit of noise when you crop the image. Again, that really shouldn't matter, but it's small. But why is May underestimated? Is it can we just say, it's demographics? Or is it something else? She does moisturize. She's particular about a moisturizing product. But yeah, so there's a research question. Some people look young. Now this one, and I should back up and point out that nobody in this slide is in the demographic groups that most of the people in this room are concerned with, right? We're all concerned with teenagers, young adults, right? and younger. Adults, all of this is that part of the age spectrum is kind of irrelevant commercially from a legislative point of view, from an applications point of view. But again, here's another person who is sort of irrelevant in this category, and it's to do with sun damage. 2 twins born on the same day, and you've got plus 4 years, plus 11 years. Sun damage does bad things for age estimation. Does anybody care? Given the commercial uses of the technology at the moment, probably not, but still it shouldn't happen. Okay, so we have these error distributions, and we don't normally plot them this way, but the mean absolute error is the standard metric, and you can see the width of those distributions is narrow in young people, and it gets older, right? So some old people look after themselves, some don't, and those age distributions get broader. To our advantage, for the most applications that we're concerned with, the error distributions are narrower in young people. Well, that's good. And obviously, it goes with the idea that with a baby, we can tell a baby's age to within, 3 months. If you're a young mother, you're probably better at it than I am, and you can figure age very well. You can do it for a 5-year-old quite well. So these error distributions get broader naturally, but there's some offsets between men and women. All right, and there's some offsets demographically which aren't that visible on this presentation, but there's a snapshot of that same graph: 18 to 23-year-olds, 18 to 24-year-olds, and you can see the red curve for women is offset that way, and I think that means overestimating age of women, not underestimating. So I've got a typo. But you would hope these things everything is normally distributed, right? This is a toy distribution. That is a toy distribution over there that's skewed, that I put on there. And what we evidently have is some skew. Now, why does that occur? Why is that distribution shifting to the right? Again, the developer's job is to think about this. It's not really my job, but I'm happy to produce data to allow people to think about this. It could be cosmetics. Right? It could be typos on dates. So key data entry on birth certificates 25 years ago, okay. It could be, in certain cases, the birth certificate was absent. If you go to the global south, particularly 50 years ago, people didn't have documents. They guessed at their age. They still guess at their age. These people are still around. There could be documentary fraud. You could present a birth certificate when you immigrate to the United States that has been razor bladed and changed, right? So you're 4 years older or younger than you want to be, or that you were. There could be natural outliers. There could be plastic surgery, which I haven't covered on here. And all of those different things do different things to these distributions. They might just appear as a one item in the long tail of the distribution. If there was a typo between 1982 and 1928, that would be a 60-year offset, right? That would be very far in the tail of this distribution. But plastic surgery, what's that going to get you? 5 years? I don't know. I should try it and see. We are thinking about this, and we would like to produce better data than we have on what's in those tails so that it can be addressed, so that May can look older than the age estimation algorithms say she does. Okay. We have recently reported, Kai said that we've got a new API. The new API allows software to be given the question, is this face over the age of 18 or 21? And it reports a confidence score. It doesn't report an age estimate. All it says is over 18 or not, right? So this is type 1, type 2 error rates. Did I pick a good president or not? Did I pick a good hotel or not? Is this radiograph cancerous or not? Decision theory 101, you can do false positives, you can do false negatives. I don't know if I'm out of time, but so we have started charting the error trade-off characteristics, standard vanilla reporting, 3 different algorithms here. Yoti is doing the best on this thing. And we can summarize that by tabulating numbers at a particular false positive rate. People under the age of 18 being classified as over the age of 18. And the developers can, of course, address this and compete. The reason to do this separately from age estimation is because different AI algorithms or different machine learning algorithms can be used underneath inside the black box to do this kind of task from absolute age estimation. Just deciding whether somebody's over the age of 18 is not deciding how old they are in an absolute sense. All right. Yeah, we can do that for men and women. I don't know why I included that slide. A different way to tabulate this, and a more operational way to tabulate exactly the same data, is to plot it against score threshold on this axis, so that you can read off either the false negative rate or the false positive rate. And you can say, if I set my threshold to be 4, what would the error rate be? If I set my threshold higher, what would it be? So you can read off threshold values. And that's what people have to do when they field these things operationally. Now, this is a chart over a fixed database of how mean absolute error increases for every single age group. Older people, it's more difficult and we don't care. The real action is down in this part of the age spectrum from 14 up to, say, 25. but you'll notice we've got a gap here. So we have a new data set coming, which I hope to be able to give you lots of details on, but it didn't happen this week. And anyway, that new data set is full age spectrum, but it goes from 0 up. Moreover, it's a global population. We've used the data set for the last 2 years, which is just Mexican, because Mexico is the largest source of immigration data into the United States. We used it, but has no demographic variability really at all. It doesn't have much, and so we expect to be able to deploy soon a very large data set, and particularly for the age groups below age 13. And through the teenage years. So there's a new data set coming. I don't think I'm going to cover this one. If I give you an image and I say, guess the age, that's one thing. If I give you a reference image where we know the age, an earlier image, and then I say, there's this new image, can you do better? Well, yes, you can, and you can do better quite substantially. And that's what this is showing. The error rate with 2 images is lower than the error rate with 1 image. But commercially, you don't often have that reference image on hand. Now, some companies probably would have, or some applications would have. Maybe social media has got an image that they trust taken 10 years ago. So you may be able to do better. This is a kind of a niche aspect of what we do, but we're doing it anyway. This is a demonstration that works, and it works quite substantially well for Kai and I. There was a conference a couple of weeks ago, and at this conference it was a virtual conference, and somebody was saying that you need to have what's called ternary logic. So you don't make a decision over the 18 or not. You say definitely over 21, maybe under the age of 18, or a gray zone in the middle where you're going to do some other form of authentication. So essentially you have 2 thresholds. You have these 2 gray, and ideally you would like to shrink that gray zone and do fully automatic operation. But if you can't do that, then you have to open up those 2 thresholds where you can be reasonably sure below 18, definitely sure above 18, and you'll do something else in the middle. That kind of metric we haven't really put into our reports yet, but we're thinking about it. So again, a future-looking activity. So just in summary, our age estimation and verification program is a facility that's open particularly to developers, but also to policymakers and end users to get an independent assessment of relative accuracy of an algorithm relative to its peers, but also an absolute statement of accuracy. How well does this age estimation stuff work? And so we allow participation every 4 months. That's about the development schedule that these developers might run by. We want to evolve this with better visualizations, better data sets, maybe better metrics. And we will chart gains by developers and report back. We think further gains are possible. There has certainly been a broadening of the industrial base here. We have 2 new developers that have just come to us this week, one from Europe, one from the United States, that are going to participate in this. So the benchmark is open. We continue to add new data into it. The challenges, as I said, are these nuisance noise factors. I think error rates can come down if you can address those. Demographics remains in some measure a problem. And of course, the big scope around this is that we're not testing in this benchmark circumvention. So all those things about injection attack, presentation attack, is somebody wearing a face mask? Are they not even real? All of that is essential in many, many applications of this technology, not all applications. But we've looked at that previously, but not in this project. And you will need to do that. Okay.
Thanks. Thank you very much indeed. That was absolutely fascinating. you can see how, from the point of view of the app developers, getting to a point where you've got an exceptionally high level of certainty around particular ages or data points or whatever would be a great position for them to be in, because then you also know where you only need to take extra steps in relation to other data points. So it's not, you don't have to do the same heavier kind of estimation or verification in relation to everybody, but you may need to take extra steps in relation to those bits of the data where you know there are higher levels of error likely. But can I ask you, what was your motivation, or what was NIST's motivation for getting into this subject area in the first place? Was it by any chance linked to the FTC's reviews of the way the copper legislation was working and the way in which that ridiculous 13 age level was set based on research in 1997 that was done to set the copper lower limit before social media existed? So what was how did you get into this topic in the first place, just out of interest?
It really wasn't that. We have talked to the FTC. We've talked to a lot of regulators around the world, but that is not the genesis of this. The genesis of this really was we collaborate with the immigration people on, is face recognition good? Along the way, they occasionally get instances of refugees, undocumented individuals, child trafficking, and they want to know age and does it work or not? And the marginal cost of us being able to do this evaluation on top of what we were already doing was quite small. So why not?
Any other questions or comments? I got A-level statistics, by the way, so I did understand at least 5% of what was there. No, well, that's great. Honestly, that was truly fascinating and great.